In this video, I will teach you about alcohols and phenols. We'll go over naming alcohols, then I will do a review of some topics from last semester on how to make alcohols and how to convert alcohols to alkyl halides. Then we'll look at the reduction of carbonyl compounds to form alcohols, then a Grignard reaction, the oxidation of alcohols and phenols, and finally we'll end up with biological redox reactions. Alcohols possess a hydroxyl group, an OH group, and these are extremely common in natural compounds. So here are some examples of naturally occurring alcohols. Phenols possess a hydroxyl group directly attached to a benzene ring. Technically, phenols and alcohols are different compounds. Here are some compounds that have phenols in them, such as dopamine. This is going to be important in looking at addiction and pain relief. Also, this compound, which is present in poison ivy. Also, phenols are present in flavonoid compounds, which are compounds that I personally work with in my research. Flavonoids are polyphenolic compounds, and one example of one that I'm working with looks like this. So that has two phenol rings in the structure. And this is called naringenin. Alcohols are named using the same procedure we have used previously. You identify the parent chain, which is the longest carbon chain that includes the OH group. You identify and name the substituents. You want to assign a locant to each substituent, giving the carbon that the OH is attached to the lowest number possible. Then you list the numbered substituents before the parent name in alphabetical order, ignoring prefix except iso and cyclo. And then the OH locant is placed either just before the parent name or just before the OL suffix. So for example, here we have a 5-carbon parent chain. So we take the pentane parent name, we take the E off and add OL to indicate there is an alcohol. For this example, the parent would be hexanol. So notice here you want to use the longest chain that includes the carbon attached to the OH. So the longest chain would not be this chain going here because you would avoid the carbon with the OH and you need to include it. Then you assign a locant to each substituent, giving the carbon that the OH is attached to the lowest possible number. So if we look at this molecule, we would number from left to right because then the OH will be on carbon 2. And if we numbered this incorrect way, the OH would be on a higher numbered carbon. The locant is then placed either before the parent name or just before the suffix. So this could be either 3-pentanol or pentane 3-ol. And remember, whenever you transition from number to letter, you use a hyphen. For cyclic alcohols, the OH group is always on carbon 1. So this would be cyclopentanol, and you don't have to then indicate that it's on carbon 1 because that's assumed. This would be R3,3-dimethylcyclopentanol. So you number with this being carbon 1 in this direction because that gives the next substituents the lower possible number. If you numbered in the clockwise directions, that would be at carbon 4, which is a higher number. So there's two methyl groups, therefore you say dimethyl, and they're both on carbon 3, so you use that number twice. And then you have to also indicate the stereochemistry of any chiral centers in your molecule. Common names for some alcohols are also frequently used. Isopropyl alcohol, rubbing alcohol, is the same as 2-propanol. Tert-butyl alcohol is often used instead of 2-methyl-2-propanol. And then benzyl alcohol is often the name used instead of phenylmethanol. Like halides, alcohols are often classified by the type of carbon they are attached to. If the carbon they are attached to is only attached to one other carbon, it's a primary alcohol. If that carbon is attached to 2 other carbons, it's secondary, and if it's attached to 3 carbons, it's tertiary. And we can often abbreviate this as the number with a degree symbol. When an OH is attached to a benzene ring, the parent name is phenol. And then if you have additional substituents, you would number so that the first substituent gets the lowest possible number. So this becomes 4-chloro-2-nitrophenol because an NO2 group is a nitro group. Of the commercially important alcohols, methanol is the simplest, and about 2 billion gallons of methanol is made every year. It is poisonous. If you ingested it, it will cause blindness, but it has many uses, including as a solvent, as a precursor for chemical syntheses, and as fuel. You may have heard that with some of the COVID sanitizers, there have been contaminations with methanol, and there have been warnings on the news about not ingesting hand sanitizer due to possible methanol contamination. Ethanol you're familiar with. It's produced by fermentation of grains or fruits. Industrially, it's made via an acid-catalyzed hydration of ethylene. U.S. alone, about 5 billion gallons are produced per year. It's used as a solvent, as a precursor for chemical syntheses, fuel, and it is denatured. However, for human consumption, ethanol must be suitable for drinking and is heavily taxed. Isopropanol, also known as rubbing alcohol, is made industrially from the acid-catalyzed hydration of propylene. So that's propylene, and in the presence of acid and water, you can form isopropanol. It is poisonous, but has many uses as an industrial solvent, antiseptic, and gasoline additive. The OH of an alcohol has a big effect on its physical properties. So if we look at these three molecules, notice what happens with the boiling point. With ethane, the boiling point is minus 89 degrees Celsius. When you swap out the hydrogen for chlorine, now your boiling point is 20 degrees Celsius. But with an OH group, it's now 78 degrees Celsius. So that's the boiling point of ethanol. And the reason for that is the hydrogen bonding. The hydrogen bonding, those are strong intermolecular forces that have to be broken in order for the phase transition from liquid to gas. So it takes more energy in the form of heat to break hydrogen bonds to facilitate that phase transition. Alcohols with 3 carbons or less tend to be miscible in water, meaning they mix with water. Alcohols with large carbon chains do not readily mix with water and will form 2 layers if you try to mix them with water. Alcohols can be deprotonated with a strong base, and in comparison to an alcohol, a phenol is more acidic by 8 pKa units, which means 10 to the 8th, which is millions of times more acidic. And the reason for this is that if you look at the conjugate base formed of phenol, it's resonance stabilized. And generally speaking, the stronger the acid, the weaker its conjugate base. So the conjugate base of phenol, due to its resonance stabilization, is a lot weaker than the conjugate base of cyclohexanol, which explains the acidity difference. Last semester, we mentioned 3 different ways from alkenes to create alcohols. One was to use acid and water. However, that had a lot of drawbacks, including rearrangements that can take place. The other was the oxymercuration-demercuration, which followed Markovnikov's rule, and the third was hydroboration oxidation, which followed anti-Markovnikov selectivity. So recall here that the OH is on the less substituted carbon of the starting alkene, and here the OH is on the more substituted carbon of the starting alkene. Also, last semester, we talked about converting alcohols to alkyl halides. So if you have a tertiary alcohol, you can use HBr or HCl to convert that to the halide. So here we have T-butyl alcohol. We can use HBr to convert that to the bromide. If instead we wanted to convert it to the chloride, we would have used HCl. Also, as a review, last semester, I mentioned that primary and secondary alcohols can also be converted to alkyl halides, but you have to use different reagents. To convert to the chloride, you use SOCl2 called thionyl chloride, which is a sulfur double bonded to oxygen and bonded to 2 chlorines. And then the PY stands for pyridine, which is going to act as a base in the mechanism. It's essentially a benzene ring, but with a nitrogen in place of one of the carbons. And then PBr3 is how you convert a secondary or primary alcohol into the bromide. Now, the new method that you're going to learn is how to prepare alcohols via a reduction reaction. And in particular, we're going to reduce a carbonyl. Reductions involve a change in oxidation state. An oxidation state is simply a method of electron bookkeeping. To determine the oxidation state of an atom, imagine the electrons in the bond as a lone pair on the more electronegative atom. So here, if we look at methanol, if we treated all bonds as purely covalent, we would break them homolytically and give every atom one of the 2 electrons. But instead, let's treat them as ionic and give both the electrons in each bond to the more electronegative atom. So if we do that, carbon is more electronegative than hydrogen, so it would give all of the electrons in the bonds with the hydrogen, but oxygen is more electronegative than carbon, so it would get those 2 electrons. Now, how do you figure out the final oxidation state? Well, you look at the number of electrons around the carbon, so in this case it's 6, and you subtract that from the number of electrons carbon will naturally have, which you get from the column that it's in the periodic table, so the number of valence electrons. So that would be 4. So 4 minus 6 equals minus 2. Therefore, that carbon has an oxidation state of minus 2. So a carbon's oxidation state can range from minus 4 to plus 4. If it's oxidizing, then it's going to be going to a higher oxidation state, so from left to right. If it's getting reduced, then it's going to a lower oxidation state. So if we look at formaldehyde, for example, and we use the strategy I just showed you, we're going to have carbon keep the 2 electrons that it had with hydrogen, and then oxygen, because oxygen is more electronegative than carbon, will keep both of the electrons that were in each of the 2 bonds it had with the carbon, and it already had 2 lone pairs. So in this example, carbon has 4 electrons. It's owning 4 electrons. So 4 subtracted from the valence, which is 4, is 0. So that's an oxidation state of 0. So converting a carbonyl to an alcohol requires a reducing agent. That's something that facilitates a reduction. If something's reduced, then something must always be oxidized. The 2 go hand in hand. So in this type of a reaction, whatever the agent is oxidized in the process. There are 3 reducing agents that can be used. The first is hydrogen gas with a metal. However, this is rarely used because very high temperatures and pressures are required. And you may recall that we did use this in converting double bonds to single bonds last semester. The next 2 are what are called hydride reagents. A hydride is simply a hydrogen with 2 electrons and a negative charge. So with sodium borohydride, we can convert aldehydes and ketones into the corresponding alcohol. So sodium borohydride is the active reagent, and then we typically use one of these solvents. Sodium borohydride is a source of hydride, H-, which does a nucleophilic addition to the carbonyl carbon, followed by a proton transfer from the solvent. So in this reaction, the hydride is going to be delivered from the reagent to the carbonyl carbon, and then simultaneously these 2 electrons form a 3rd lone pair on the oxygen. Now you can think of this mechanism as just being H-, even though it is connected to the boron atom in the reagent. It is easier to think of these mechanisms as an H- acting freely to attack the carbonyl carbon. And why would it attack the carbonyl carbon? Tell me in the chat why you think it would attack, why H- would be attracted to the carbonyl carbon. So you get to this intermediate, which then grabs a proton from the solvent. If you have an unsymmetrical ketone, you can get a chiral center, and you will get both enantiomers. The second type of hydride reagent is lithium aluminum hydride, often abbreviated as LAH or like this. And this is a very strong reagent. It's stronger than sodium borohydride. So in this example, it is also reducing an aldehyde to the corresponding alcohol. And if you look at the structures of the reagents, they're very similar. They both have a central atom. In this case, it's aluminum surrounded by 4 hydrogens. With sodium borohydride, you have a boron in the center. But LAH is much more reactive than sodium borohydride. Because it's so reactive, it can't be used in the presence of a protic solvent, and the proton source has to be added after the carbonyl is reduced. So the same mechanism here, the hydride attacks the carbonyl carbon, and those 2 electrons form a third lone pair. And then after that's completed, then you can add water or some proton source to get the hydrogen on the O-. And there are a wide variety of hydride reagents that can be fine-tuned by using various R groups on the aluminum or the boron. Lithium aluminum hydride is strong enough to reduce esters and carboxylic acids, whereas NaBH4, sodium borohydride, is not. So if you have a carboxylic acid, this carbon will be, that's this carbon here, will be reduced to the alcohol. This carbonyl carbon of the ester, notice it's also reduced to the alcohol. So the reduction of carboxylic acids and esters yield primary alcohols. The way this works is that we're going to have 2 hydride additions, which is why we're going to need 2 equivalents of the hydride. So the first step is the same as we've seen, but the intermediate collapses, kicking off the methoxide, so that you get this aldehyde intermediate. The aldehyde is then attacked again by a second equivalent of the hydride, and then followed by proton transfer, you get your alcohol. Another type of reaction is the Grignard reaction. And with this, you have a Grignard reagent which has some organic carbon-containing group attached to magnesium, which is attached to a halogen, typically bromine or chlorine. So here we can make these by taking the organohalide and adding magnesium ribbon. So if we take bromobenzene and add magnesium, now we have a Grignard reagent. If we take propyl chloride and we add magnesium, now we have a Grignard reagent. Carbon is a lot more electronegative than magnesium, so essentially that carbon attached to the magnesium is going to be partially negative and will behave like a carbon anion. So while the bond isn't completely ionic, we can think of it like this. So just like the hydride attacked the carbonyl carbon, the Grignard is going to attack the carbonyl carbon. And you're going to see a lot of reactions this semester with some nucleophile attacking a carbonyl. This is a very, very common pattern of reactivity. So here the negatively charged Grignard, which is abbreviated as R, is attacking the carbonyl carbon, forming a new bond, breaking the pi bond of the carbonyl to get to this intermediate, which followed by an aqueous workup is protonated. So the important difference here is you're creating a new carbon-carbon bond, not a new carbon-hydrogen bond. Because the Grignard is both a strong base and a strong nucleophile, it will be quenched with water or alcohol. So if you are doing this reaction in the lab, you have to make sure that you don't have any water in your flasks, in your glassware, in your solvents. So we typically use anhydrous ethers for Grignard reactions. And here are some examples of Grignard reactions. Notice when you have an ester that you actually will add the Grignard twice for the same reason that the hydride added twice. As I mentioned, Grignards are not compatible with proton sources, so OH groups or water. So if you tried to do this reaction shown here, it wouldn't work because this hypothetical Grignard couldn't be formed. It would just immediately react with the H of the OH. And this will happen a lot where one functional group is incompatible with a reagent you are using. So there's a way around this called protection. So in this scheme, what we're going to do is first protect the alcohol using what's called a protecting group, then do our reaction, then deprotect. One such protecting group is trimethylsilyl. That's a silicon atom with 3 methyls on it. So if we protect this alcohol, we're going to remove the hydrogen and add on that TMS group. So we protect the alcohol, then we do whatever we want with the rest of the molecule, and then when we're ready, we can remove the protecting group. And fluoride ions are often used, as is acid. For phenols, they are prepared industrially as shown here, and 2 million tons of phenol are produced industrially every year. And phenol is a precursor in many chemical syntheses, and these would be syntheses to make things such as drugs and polymers, food preservatives, etc. So since you can reduce carbonyls to alcohols, what about going the other direction, oxidizing alcohols to carbonyls? You can do that as well, and I'm going to show you several reagents. So first of all, if you have a primary alcohol, you can oxidize it either to the aldehyde or to the carboxylic acid, depending upon the reagent you use. If you have a secondary alcohol, they will only ever produce a ketone no matter what you use. So this is important. Tertiary alcohols generally do not undergo oxidation because they don't have any protons at the alpha position. The most common oxidizing agent is chromic acid, which is also called the Jones reagent. And it is formed either from chromium trioxide in the presence of acid and acetone, or sodium dichromate in the presence of acid and water. You don't need to know this mechanism, but essentially a chromate ester is formed, which is then eliminated to form the pi bond of the carbonyl. What you do need to know is that chromic acid will oxidize a primary alcohol all the way to a carboxylic acid. It won't stop at the aldehyde stage. However, PCC, pyridinium chlorochromate, shown here, will stop at the aldehyde. Regardless of which oxidant is used, a secondary alcohol will only go to the ketone. And that's because it just has one hydrogen there to be removed. Another oxidation is the Sworn oxidation that uses dimethyl sulfoxide and oxalyl chloride, and the mechanism is shown here, which you also don't need to know. And this is a continuation of that mechanism. You can look at it if you're curious, but I won't test you on it. The important thing to know is that the Sworn oxidation is going to be just like PCC, where it converts a primary alcohol to an aldehyde. Finally, the Des-Martin periodane oxidation, DMP, is similar to the Sworn oxidation in that it will take a primary alcohol to an aldehyde. This is believed to proceed through this periodinane intermediate, but again, I won't test you on this mechanism. Nature regularly employs reducing and oxidizing agents. NADH is a reducing agent. This is the chemical structure of NADH. Essentially, NADH is a hydride delivery agent. So this hydrogen is delivered to a carbonyl and reduces the carbonyl. And this is one way that nature converts carbonyls into alcohols. NAD+ is an oxidant and undergoes the reverse process. So alcohols can be oxidized to the carbonyl by using NAD+. And the two of these play a key role in metabolism. Recall that tertiary alcohols do not undergo oxidation because they lack an alpha proton. You might expect phenol to be similarly unreactive because there's no hydrogen on that carbon. However, they are even more readily oxidized than primary or secondary alcohols. Phenol oxidizes to form benzoquinone, which can in turn be reduced to hydroquinone. This is a large overview of several synthesis strategies, looking at a lot of different reactions you've learned. So you can take an alkyne to a ketone or an aldehyde. That's a reaction from last semester. You can convert alkynes to alkenes using reactions from last semester, alkenes to alkanes using reactions from last semester, alkenes to alcohols using reactions from last semester, alcohols to alkenes using reactions from last semester. And then here are some new ones. You can go from an alcohol to a ketone or aldehyde using our new reagents, chromic acid, PCC, DMP, or SWERN. Now, if it's a primary alcohol and you're using chromic acid, you will get the carboxylic acid. You can go the other direction and reduce them. Last semester, you learned how to convert alcohols to alkyl halides. Also, you learned how to take alkanes to alkyl halides using radical reactions. So this is just simply an overview of things from last semester and how it can fit into what we're learning this semester. So here are 3 questions. The first one is, what is the product of the following reaction? So we're using sodium borohydride. So you need to recall what types of functional groups does sodium borohydride react with. So pick your choice, A, B, C, or D, and let me know in the chat. For this reaction, what is the product? So here you're using a Grignard reagent. So the Grignard is an ethyl Grignard. So what will it produce when you react it with this ketone? Finally, if you react this diol, it has 2 OH groups with excess PCC, what type of reaction product will you get? A, B, C, or D? Let me know in the chat. And that's it for this video.